Five-number summaries are another set of descriptive statistics that we can use to describe the distribution of a continuous variable that we may be working with. And we've seen this in passing in previous videos when we're working with continuous variables. If you recall, if we use the summary function on our continuous variable, in this example, let's take a look at music perception scores. Here we see the minimum value, the first quartile, the median, the mean, the third quartile, and the maximum value of the distribution. In order to clean this up, let's pass this through the round function. And so the values that we're most familiar with at this point are the minimum value, which is negative 0.67, the maximum value, which is 0.53, the mean, which is 0, and the median, which is negative 0.02. In addition, we have two other values here, the first quartile and the third quartile. What we're working with here are called five-number summaries. However, we see 6 values. In this particular case, the mean is not something we're going to be looking at, particularly because it's susceptible to any outliers that we may have in our distribution. So any extreme low values or any extreme high values. In other words, skewness affects the interpretation of our mean. So if we get rid of the mean, we have our minimum, our first quartile, our median, our third quartile, and our maximum value. So with five-number summaries, there's often confusion with 3 different terms: the quartile, the quantile, and the percentile. So those are 3 different terms that we're going to be using throughout this video, and it's important that we clarify what those specific terms mean, because you might often see misinterpretation of those particular terms in the research literature. So first, let's talk about quartiles. So the quartiles describe the exact cut points that break the distribution up into 4 equal parts. So the first quartile is the exact value that demarcates the first 25% of the distribution. In other words, if we rank order our distribution from the lowest value to the highest value, the first quartile is the value that demarcates the first 25% of the distribution. Or another way to think about this is 25% of the distribution sits below this value. The second quartile is the exact value that demarcates the first 50% of the distribution. This is also called the median. The third quartile is the exact value that demarcates the first 75% of the distribution. And the fourth quartile is the exact value that demarcates the first 100% of the distribution. So here the first quartile is negative 0.12. The second quartile is negative 0.02. The third quartile is 0.10. And the fourth quartile is 0.53. So what's important to note here is that when we use the term quartile, it specifically refers to the numerical values. Now the term quantile is often confounded with the term quartile, but they're 2 separate things. A quartile is a special version of a quantile. So a quantile is any integer ranging from the value of 1 to 99. So when we were talking about quartiles, the first quartile in this distribution is negative 0.12. And that represents the first 25% of the distribution. When we're talking about quantiles, the 25th quantile of the distribution is equal to the first quartile. So here, the 25th quantile of the distribution is equal to negative 0.12. The 50th quantile of the distribution is equal to our median, which is negative 0.02. Our 75th quantile of our distribution is equal to the third quartile, which is equal to the value 0.10. Now we can identify the quantiles of any given distribution by using the quantile function. So the first thing we want to do is pass in the variable that we're interested in. So again, let's use the music perception scores variable. And then we're going to use the argument probs. So for instance, if we take a look at our first quartile, which is also equal to our 25th quantile, note we need to specify our quantile as a decimal. And we see we get the value of negative 0.12, which is also equal to the first quartile. Let's do the same thing, only let's take a look at the 50th quantile. Here we see it's equal to the median, which is negative 0.02. If we take a look at the 75th quantile, it's equal to the value of 0.1, which is also equal to our third quartile. And so you get the idea. Here we can take a look at any quantile value. So let's take a look at our 99th quantile. Our 99th quantile is equal to the value of 0.41. Our 33rd quantile, or the value where 33% of the distribution falls below, we see that rounded, the value is negative 0.1. Now, one thing we may want to do if we're working with educational tests is report all of the values of the distribution as they relate to their percentile ranks. So percentile ranks are synonymous with quantiles. Only here, when we use the term percentile, we're not talking about the score that's associated with the quantile, but we're talking about the actual quantile number. So 1%, 2%, 25%, 75%. So again, to make the distinction, when we're talking about quartiles or quantiles, we're talking about the value within the distribution. When we're talking about percentiles, we're talking about the percentage as it relates to the distribution. And common uses of the percentile is in standardized testing. So your score may fall at the 75th percentile, or your score may fall at the 90th percentile. And another common use of the percentile is children's height. So if any of you have children and you've been to the doctor with your child, they'll provide you the height of your child, and then they'll also indicate what percentile they fall in. And the benefit of examining a quantile value associated with a percentile value is that it allows us to compare one score in a distribution to all the other scores within the same distribution. So if we want to provide the 100 percentiles and the quantile values associated with those percentile ranks, we're going to use the CTT package for that. I already have it installed on my computer, so I'm simply going to load it using the library function. And when we do this, this is a two-step process. First, the function is going to standardize all of the values in our distribution to what's called z-scores. Because it's standardized, it allows us to compare apples to oranges. So as an example, our music perception scores are on a different scale than our music aptitude scores. Let's say we wanted to look at a student's percentile ranking and compare that student across both tests, the music perception test and the music aptitude test. In order to make that comparison, what we have to do is standardize them. Because remember the normal distribution. A standardized normal distribution has a mean of 0 and a standard deviation of 1. If we take a look at the mean of our music perception scores variable and compare it to the mean of our music aptitude scores, we see that it's a different mean. Now if we take a look at the standard deviation of our music perception scores and compare it to the standard deviation of our music aptitude scores, we see that there's a different standard deviation. So because they have different means and different standard deviations, we cannot meaningfully compare these two variables. So what we have to do is transform them to a standardized distribution of a mean of 0 and a standard deviation of 1. So a z-score is the standardization of any set of scores where it's changed to the mean of 0 and a standard deviation of 1. And again, this allows us to compare these scores to any other sets of scores. Now, it's also important to note that this particular function standardizes the scores and then it provides the percentiles. That's not necessary in order to calculate the percentiles. As we've seen, we can calculate any of the quantiles and their related percentiles simply by using the quantile function. Because here, commonly when we use this package, we're usually working with either psychological or educational data, where we are commonly interested in comparing different variables or different sets of test scores. As part of the process, it also provides for us the z-scores. And we're going to be talking a little bit more about z-scores in a later video. But we're simply using this function because it's the easiest way for us to access each of the percentiles along with their corresponding quantile values. So again, this function is first going to transform the data to z-scores, and then it'll provide for us the percentile ranks. So let's store this in an object. We'll call it MP for music perception transform. And here we're going to use the score.transform function from the CTT package. And then what we'll do is we'll pass in our variable of interest, music perception scores. Now, if we want to take a look at the transformed z-scores, we can call on the new.scores attribute. In other words, we're going to take a look at our object. We'll use the $ notation, and then we'll look at the new.scores attribute. So here you see all of the values within our distribution have been transformed to z-scores. Now again, remember that z-scores have a mean of 0 and a standard deviation of 1. We can check this by using the mean function. And here we have a value of 0. So this is scientific notation that basically says it's 6.4, but then add 17 zeros to the left. So that's a very, very small number. And we would interpret that as 0. And then if we take a look at the standard deviation, we have a standard deviation of 1. So again, we're looking at the z-score transformation of our distribution. Now, if we want to take a look at the percentiles, we're going to use the p.scores attribute. So again, let's take a look at the object, MP transform, and then we'll take a look at the p.scores attribute. Now let's round this to make it look a little bit cleaner. So these are our percentile ranks for each of the scores within our distribution. So to make this a little bit clearer, let's take a look at our original distribution. And then what I'm going to do is I'm going to use the round function to make it a little bit cleaner. And then again, let's take a look at our z-score distribution. And then again, let's round it to make it look a little cleaner. Okay, so here we have our three values. Here we have our original values from our distribution. We have our z-scores, and we have our percentile ranks. So the original value in our distribution, which is negative 0.67, we changed to a standardized score of negative 3.82. And this is equal to our first percentile. So these are given as decimals, but we refer to them as percentages. So 1%. This is our first percentile. Our second score in our original distribution was 0.31. It was standardized to a value of 1.78. And we see here that it's our 95th percentile. So what this does is it allows us to provide our data in terms of standardized units or percentile ranks. Now, if we want to report what the values are for each of the percentiles, so that way students or parents can compare the scores to the percentiles, we can use the quantile function again. We'll pass in our music perception scores, our original variable. And then we're going to use the probs argument. We're going to use the concatenation function. And then what we're going to do is we're going to set a sequence ranging from 0 to 1 by increments of 0.01. I'll run this code. And then we see all of our values that correspond to each of the percentiles. Now what we can do is clean this up a little bit. And let's move this down here. We can clean this up by passing it through the round function. And we'll set the digits to 2. And here's how we would report them. So the first percentile is the score of negative 0.32. Second percentile is equal to the value of negative 0.29. The third percentile is equal to the value of negative 0.27. Or we could call these quantiles. So the first quantile is negative 0.32. The second quantile is negative 0.29. The third quantile is negative 0.27. And so in this video, we've covered the difference between quartiles, quantiles, and percentile ranks. In addition, we've briefly touched on the definition of what a z-score is and why it's important.